I'm going to talk about localized modes, but before I go into detail, maybe you wonder why there's a palm here in the emblem of university in Germany. And that has to do with the fact that Tübingen is in the middle of Sweden. This is Germany. This is an old native town hall. This is the city of the university was founded in 1477 by Earl Eberhard. And Earl Eberhard made a trip to Pakistan. Okay, waveguides is the topic I'm going to talk about, and waveguides are, of course, well known to guide the photons and to guide phonons. An example from acoustics, everybody knows the medical application is the stethoscope, and we have hollow-coated tubes, and we have dielectric fibers, and the most noticeable property is that the dispersion relation of those modes gets modified from the dispersion relation in free space. So the free space dispersion relation, which is the case of photons and phonon resistance, gets modified, and there is a particular frequency, and below that frequency, no mode is able to propagate, and we talk about evanescent modes and so on. Actually, the Helmholtz equation eigenvalue problem is behind all that, and it has been well investigated during the last 2 centuries. Mainly in the study of acoustic theory, vibrating elastic membranes, and electromagnetic waveguides. But there are also other types of waves, for example, guided matter waves, and I remind you that we have a 2-dimensional electron gas, and in our computers they are operating very fine all the time. We have guided electron matter wave functions along such a sketchable 2-dimensional electron gas system. Also, we have matter wave guided matter waves for cold neutrons, and recently also called atoms, which can be trapped either by magnetic forces or can be trapped by electromagnetic forces and hollow-core electric fibers, or, as we have also learned, laser beams. They can be used to guide atoms and to manipulate other-sized particles and so on. And in this case, again, we have an excitation threshold. And the question I'm going to investigate is the following is now, okay, what's happening if I have crossing? 2 waveguides cross. Of course, this excitation threshold is determined by these basic tube width parameters, and if half a wavelength fits into such a tube, then we get, so to speak, an estimation for this lowest energy that can still propagate. Okay. So what we are looking for is the ground state mode of a Helmholtz, let's say, Schrödinger eigenvalue problem. Helmholtz if it's photons and phonons, and Schrödinger if it's matter waves, but it's the same mathematical problem. There's a Laplacian, and this Laplacian equals to some energy parameter psi. In the case of photons and phonons, it's of course E squared or omega squared. But that doesn't matter, it's a parameter. And the influence of the hard walls can be taken into account by many ways, by potential state or just by using directly non-linear equations. So we require that the mode is going to be 0 at the hard walls. And in this case, the separation ansatz cannot work. So really one has to look at the partial differential equation. How should one define a localized mode? It is known in mathematics that the eigenfunctions of the Laplace operator are real analytic functions which never vanish on any open set. So in practice, we must be content with saying that an eigenfunction is localized if it assumes very small values as a set complementary to the region where it is localized. So if I have, so to speak, such an extended region A, and I have a part of this region A prime, then I would say my mode is localized in this region A prime if the integral over the complement is going to be extremely small. That's a practical way to define localization. Okay, relatively speaking, our cross allows symmetries which are given by the behavioral group. And if we are just looking at solutions which are symmetric around the plane z equals 0, then we will just have AG, B2, B2U, B3U, and E1U. Those are the rest symmetries that are left. And the modes we are looking for can be classified by those symmetries. Okay. Now there is a point that needs to be mentioned regarding the spectrum of the Laplace operator. Discrete spectrum with eigenfunctions of finite norm, those are the localized ones. Then we have the continuous spectrum, which are the propagating modes. Most of you probably are well known, acquainted with that. And then we have the continuous spectrum, we have embedded eigenvalues in the continuous spectrum. I will come to that in a moment. You can have embedded discrete modes, for example, vanishing along those lines and along those lines, forming a T over an L. Okay, now the question that is also of some interest is, are we really required to look at a 3D problem? Can't we just discuss a 2D problem? Well, a thin film in that sense is not 2D, and the 2D really is a planar situation, which is a very thick film. And most of the time it doesn't matter because it will just mean shift, but in the interacting system, this of course matters. So if I, for example, just confine myself to the spectrum of the Laplacian, which is described as a particle box of widths dx, dy, and dz, then all the integers in x and y and z constitute, so to speak, the actualization of the possible energy limits. And in a realistic thin film, for example, you would have this Vz much smaller than either the name of the x and y. And if the, say, the temperature or kinetic energy of my particle is small compared to the level distance between nz equal to 2 and nz equal to 4. The motion of the particle in the low energy subspace nz equal to 1 may be considered effectively as two-dimensional. And this associated any eigenvalue of the energy eigenvalue of the particle is then two-dimensional type of kinetic energy plus this shift, corresponding just to the lowest one. If I would have now just non-interacting particles, it would be clearly enough to look in a two-dimensional problem. If I would have interactions, it would not be enough, and I would always be required to look at this three-dimensional problem. So the planar limit is rather the case where my system is going to fit. Okay, now I give you some examples of waveguides with broken translational invariance across L and T. Such are simple prototypes. And the modes that you can find, which determine the ground state here, are in the energy below the excitation threshold, and they are sitting around this crossing. And you wonder, how is it possible that I get a trap confined to a localized mode, although I don't have a potential for translation invariance along this axis and then on that axis. And furthermore, for any width ratio, Vy over Vx, you obtain correspondingly localization NC, but it's always existence of such modes has been, for example, shown in microwave experiments in this L-type structure. And one can see from the reflected power in such a microwave experiment nicely the existence of this bound state mode. What has not been investigated is the dependence on the width ratio here to here. And if you would do this, then you will find that this curve starts at 0.89, and for ratios below that, you would never find a trap mode. So for this L-type geometry, the localized ground-state mode exists provided Toeplitz ratios obey to this constraint. Okay. This is in a sense an interesting signature of such types, and for the T-shape, which is in a sense 2Ls, a similar phenomenon happens. You find localized ground-state modes exist provided this ratio obeys to this constraint. And when you are very near to this constraint, it's just discernible that you get a localized mode. But below, above that value, you would never find it. So in the cross-shape geometry, we always find it, whereas in the L and the T, we only find it in a certain ranges. The question is, what is the reason? And making a side remark, we have been talking in this conference about bending and about elastic energies, and there are, in a sense, generalized Laplace fields. So when you put such stuff into tubes, and the tube would approach a crossing region or a margin region, some critical values seem to exist for localization of modes. So the energy of the ground state in this case has been compared to literature values, which are in perfect agreement. So this shows that the stated algorithm that can solve such problems. Okay. So can we understand that we always find a localized mode in the case of the cross? Okay, so let's look at the kinetic energy as we go, let's say, along the blue line. So we go from below, and we are here, and then all of a sudden, this width jumps to infinity, and then it jumps back to the finite width. So there's a jump in the transversal kinetic energy. And this jump in the transversal kinetic energy I can describe by a projection with a test function that has a profile which corresponds to the true ground state wave function I calculated, and it provides for me some type of effective potential. So the variation along this line essentially can be described by an effectively one-dimensional Schrödinger type eigenvalue problem with a box-shaped potential. And this value here corresponds to the excitation threshold, and this value here depends on details, but it is lower. And as it is lower, it means that there is a binding strength, and it means that we have an attractive potential, and it means that we always have a bound state, because in a box-shaped potential, we have always at least one bound state if it's attractive. So now come the same kind of argumentation for the L. So for example, let's go in the case of this L in this direction. And we would correspondingly see that we have here the excitation threshold corresponding to the tube in this direction. And as we approach this region, the transversal kinetic energy jumps. Essentially, such a value. And then we approach the wall, and there the potential goes to infinity. So this means we have a one-dimensional eigenvalue problem, essentially, but with potential that is infinity at x equal to 0. So it corresponds to having a wave function in the box type potential, which in the middle has a 0, so it's an odd parity solution. And an odd parity solution is known to require a minimal binding strength. Okay, so the same reason in 3 dimensions, that we have a radial potential, you need a minimal binding strength to trap it. So we see in this kind of reasoning, we understand why if the tube is out of these limits, we cannot find a bound state. So this is of course well known. This is the reason why we always find an even parity bound state in the box, and this is the reason why we find an odd parity bound state only above a certain point. Okay, so let me summarize that the existence of these trapped or bound states around branching zones depends on the tube width ratios. And these are the findings presented for a Laplace operator. For a Laplace operator obeying to directly boundary conditions. If I now generalize the Laplace operator to something that twists around, let's say, two tensor, I wouldn't be too surprised if similar phenomena could be found, perhaps governing the patterns of defect formation around crossing and boundary zones. I think with these remarks I should stop. Any questions? It's like this.
Go on then. So you have this boundary condition, and then you replace it with this integral condition. I know nothing about this, but that seems slightly odd to me because you're still imposing the differential equation away from the area of interest.
Yeah, you have, let's say, you could take the example of the electromagnetic mode propagating in a hollow metal tube. And then you would have for TE waves corresponding boundary conditions, like directly from one. And approaching the crossing zone, all of a sudden that changes. So going along a projected side, you effectively see a one-dimensional potential. Because it transfers the kinetic energy and undergoes a large change. So you could say it's confinement generated by kinetic energy. We have investigated this phenomenon in the context of cold atoms, which are actually interacting. And the cold atoms then can start to populate these localized mode levels. But with a repulsive index present, that works only up to a critical particle. The surprising thing here was, if you would like to put it this way, that there is a confinement that is not induced by the gradient of potential. The binding force is not related to the gradient of potential, but is induced by the jump in the kinetic energy due to the change in the boundary condition. And I believe this phenomenon is universal enough that it can also have an influence on other gradient-like kinetic energy dominated systems, in tubular systems and in tubular-like branching zones and so on.
All right, thank you very much.